All right, in this video, we'll be going over a worked example related to the definition of density, but really working with some uncertainties here. So define density, hopefully everybody put mass per volume. Mass per volume is how we define density. It says the mass m of a metal sphere is given by the expression m equals pi d cubed rho over 6, where rho is the density of the metal and d is the diameter of the sphere. Data for the density and the mass are given in figure 1.1 there. And it says calculate the diameter d. So I will start by just copying my equation down. M equals pi d cubed rho over 6. I want to rewrite this to make the diameter the subject. And so I'd rewrite this first like d cubed equals 6m over pi rho. So far, so good. Just multiply both sides by 6 and then divide by rho and pi. So you get that. And then we want to take the cube root of both sides. And so d should just be 6m over pi rho to the 1/3. Taking a cube root is the same thing as raising it to the 1/3, but my calculator can, it's a little bit friendlier for my calculator. Some numbers now. So meters is what I'm restricted to here for distance. And so let's just make sure we got mass in kilograms, density in kilograms per cubic meter. So that all looks good. So 6 times 7.5. That's a pretty inert metal sphere. Mass and inertia, kind of like the same thing. All right, so you get 45 there divided by, I know there's got to be a pi button somewhere on this calculator. I feel like it's, let's see it. That should be good enough, right? Divided by pi, divided by 8100. And so you should have got this number as a raised to the 1/3, raised to the, here's how I put in 1/3. Just kind of spam the 0.3 there. 13.7. I could have made a mistake, so let's not.
So did I.
I mean, that's a really big sphere, so I feel like maybe did I go wrong somewhere here, class? Did anybody see a mistake? Let's check it again. 6 times the mass of 7.5 equals that, divided by 3.14159, good, divided by 8,100 equals, I feel like that's a different number than I just had a moment ago, raised to the 0.3 a bunch. Always check it again. 0.12, 09. So maybe you say 0.121. Yeah, because this seems unreasonable. Like 13 meters, that's a really large metal sphere. It's like, So always check the reasonableness. I must have, pushed the buttons a little bit. I went wrong somewhere with the button pushing. We'll check the video again. I'm recording all this. And so if you saw the mistake I made intentionally to see how closely you were paying attention, just leave it down in the comments below. I'll leave my answer as 0.12. The question goes on to read, use your answer in the data in figure 1.1 to determine the value of D with its absolute uncertainty to an appropriate number of significant figures. And so here's where we have to sort of realize that there's uncertainties in rho and in M that lead to an uncertainty in sort of the reported value here. And it's tricky because it's let's go back to this form of the equation, D cubed equals 6m over pi rho. If there's 4% uncertainty in this and 5% uncertainty in this, so there's a total of 9% uncertainty in the calculated value of D cubed. In D cubed, there's 9%. which means what's the percent uncertainty in D?
27.
No,
What?
you got to go the other way. So think about it like this. If the way that we add up percent uncertainties, right, is to say like if D had 3% uncertainty in it, right, then D cubed would have 9%, right, because we add that up.
Yeah.
And we know that there is 9% uncertainty in this. So there's 9% uncertainty in this. In other words, you got confused with when we're working the other way and we're like, oh, if pi was cubed here, then we'd triple its uncertainty. That would be the uncertainty in this. But because we're trying to figure out what is the uncertainty in this, we have to think about it like, okay, the uncertainty in these add up to 9%. Well, this is like saying, well, what's the uncertainty in each one of these, what is it, a diameter? In each one of these diameters then, if we know that the total is 9%. So each one has 3% uncertainty in it, right? 3, 6, 9, that adds up to 9%. And that's the same thing as the 9% here, like it's the same uncertainty.
So does there being 6 m's not have an effect every time multiplying that by 6?
Yeah, this number 6 doesn't have any uncertainty in it. It's exactly 6.
Yeah.
So there's no uncertainty in a coefficient like 6. There's no uncertainty in pi. We can write pi as precise as we want, 3.1. I mean, there's books that have been published it's called pi. It's like pi to 10,000 decimal places. We can calculate that as precise as we want. But the percent uncertainty in D is 3. So if we say now the data here to determine the value of D with its absolute uncertainty, we would start by realizing that because there is 9% uncertainty in this, there must be 3% uncertainty in each one of these diameters. That's how it adds up to 9. Okay. If we had the data a different way, and let's say it told us, oh, D has 3% uncertainty in it, and we'd say, what's the uncertainty in D cubed? We just add it up. Okay, so we're working sort of the other way. It's kind of like when we take the cube root here, right? Like there's 9% uncertainty underneath this radical. When we take the cube root, we're sort of dividing it by 3. So there's 3% uncertainty in one value of D. So if I take my 0.12, this number actually, okay, and multiply it by 0.03, 3% uncertainty in that, I realize that I have 0.1209, I think it was, plus or minus 0.0036, and so 0.004. So it's like my uncertainty is 0.00 in this place right here. That's where my uncertainty starts. And so I'd report my answer as 0.121 plus or minus 0.004. That's what you should get for your last 3 marks there. All right, so that's out of 5. All right. This is one, we'll take a look at the mark scheme and make sure that we've attacked this correctly, but I'm nearly certain that's correct. Part 2. Wait, how can I get out of it?
Oh, no, I know this is right. I just don't understand why. I'm not doubting.
Yeah, we have to take some time with it there. It's the idea is confusing because of the way that we add the the exponents there. But we're working back the other way. That's what we have to just sort of. Here's another bit of practice for you. Unfortunately, the mark scheme isn't much help in terms of an explanation. It just will sort of show you the answer, and you have to kind of just go for it and say, okay, well, that's right. So I'll figure it out from there. Let's do this. Let me share my screen here. Hopefully I'm not like publishing anybody's grades when I do this. I probably will actually. Okay, good. And then let's go to this thing. And this was 23 October, November 2016. So if we change the year to 2016, and we go all the way down to the winter. This was question number 1 from this year that we just took a look at there. All right, so let's give ourselves some feedback. Mass per volume, check. 0.12, I don't know how I blew that one, but yeah, we eventually got it right. The percentage uncertainty is 3% uncertainty. See, they got to divide it by 3 there, okay, because it's cubed. Then you take 3% of your calculated value, and I think that's what we said for the final answer. So that is correct. Now we'll go to, let's go ahead. Shift gears a little bit here. Now we're going to take a look at this one. All right, so let me stop the share there. This one says the volume of liquid flowing in time t through a pipe of radius r is given by an equation there. I think we might have worked with this equation, just kind of looking at base units or something. It says where P is the pressure difference between the ends of the pipe of length L, C depends on the frictional effects of the liquid. Bless you. An experiment is performed to determine C. The measurements are shown in figure 1.1. Calculate the value of C. So more practice along the same lines here. Let's kind of use the same strategy we just used a moment ago. And let's make C the subject. And so let me rewrite the equation like V over T, volume per time, equals pi P R to the 4th over 8CL. Multiply both sides by C. And then multiply both sides by T over V. That gets rid of those guys over there. And so C all by itself equals all this, pi P R 4T over 8 LV. Nice and easy. Pi, now take a look at the units here and just make, see millimeters. We got Newton seconds per square meter, are the sort of weird units of C. Meters squared, so like these millimeters are no good. Everything else looks good up here, right? So like take a look and make sure everything is like SI units. So the pi is okay. The pressure is in Pascal, or the pressure is actually in kilopascals, right? So they're telling us pressure measured in thousands of pascals, so 10 to the 3. It's like 2.5 kilopascals, okay? Likewise here, this is micro. The flow rate is in micro cubic meters. You know, they put a factor of 10 to the 6 in there. So that's kind of tricky. So let's write it like this. The pressure is 2.5 by 10 to the 3. The radius is 0.75 by 10 to the negative 3. That milli means 10 to the negative 3, and then that whole quantity is to the 4th power. So this is kind of tricky to keep track of that, right? And then T, great, they give us V over T. They don't even give us T and V. So we know V over T in micro cubic meters per second. So we'd have to just take the inverse of this, right? So it's T over V. So I kind of just remind myself that if V over T is equal to 1.2 by 10 to the negative 6 cubic meters per second, then T over V is going to be that number. And I just type it in my calculator like this, 1.2 times 10 raised to the negative 6. So that's the number. And then hey, there's pi. So above my x squared here, above my x squared, you see that 1 over x? That's the inverse key. You might have an x to the -1. See, there's that pi right there. I didn't see it before. All right, so I'm going to hit shift or second, 1 over x. And so that right there, that's got to be t over v. All right, because I just took the inverse of this, right? So v over t is that, then t over v is the, 1 over that, the inverse. And so that's that number. It's 833,333. So keep in mind that that's t over v. Like I'm taking care of both of those when I substitute this number in. I'm plugging in t over v. So that number is 833,333.3, and those go on. Over, I already got my v taken care of, got an 8 down there. I got a length in meters. All right, so I think that should get it. That's hard enough to, get those numbers right. So it's easy to make a button pushing mistake. I'm going to use the newfound pi. There we go. Times, open parentheses, 2.5 by 10 to the third, close the parentheses, equals, taking care of those two. Now I got to multiply by, so times, open parentheses. I'm going to open parentheses twice on this and go 0.75 by 10 raised to the -3, close them once, raise it to the 4th power, close it again, equals. Now here, I really feel like that the answer, if you had a better calculator, will not be this. And now I should take the time to show everybody. See how I have this button right here that says FE? So that's like turn it into engineering mode. And so I think if I hit it, that's actually the number that my calculator knows that to be. In other words, in scientific notation, in engineering mode, it's 2.5 by 10 to the 9, right? When I had it like this, it just rounds it to the 2. So take care of that, okay? We've run into that before where like your calculator, if this looks like, oh, my calculator has a significant digit in the very last place in its display, you probably need to find a way to convert it to engineering mode. So you see, oh, wait, that number is actually this. Okay, it's just they rounded it to the last place. So that's the actual sort of answer that I've got so far. And I'm only at sort of this term here. I still got to multiply by 833,333.33333 equals, divided by 8 equals, divided by 0.25. And I'm getting an answer here of 1.035 by 10 to the -3, it looks like.
Hey, Dr. Schley,
Yes.
we got a different answer again. We got 0.0000647.
You both got that?
Yeah.
Yeah.
I mean, I don't see a mistake in the calculation. I could have pushed the buttons wrong. So we'll check the mark scheme in just
I
a
got the
second.
same answer as you, but I forgot to convert millimeters. So I got.
Okay. Well, millimeters is to the 4th power, and so that affects the calculation, pretty dramatically. So we'll check the mark scheme in just a second, guys. Calculate the uncertainty in C. So here we've got absolute uncertainties in measured values, and so we'd really have to calculate the percent uncertainty in V over T, or T over V in this case, in R, in L, and in P. Like we need the percent uncertainty in all of these, and then we add them up. Okay, calculate the uncertainty in C. Now, do they want a percent uncertainty or an absolute uncertainty? State the value of C and its uncertainty, the appropriate number. So here I imagine a percent uncertainty would be fine, and then we could take that percent of this value and report it as the absolute. If I am wrong, I would lose the marks here, but I might get an error carried forward for the rest of it, right? So I'll stick with my solution here. 1.035 by 10 to the -3. All right, real quick, let's take a look at V over T has a percent uncertainty of. It's going to be 0.01 divided by 1.2. And since both things are times 10 to the negative 6, those would just cancel. And so times 100, and I've got a 0.83% uncertainty from this. For pressure, I've got 0.05 absolute divided by measured value 2.5. And again, the times 10 to the 3 just would cancel out. So we just really were like this divided by that times 100. And so there's 2% from the pressure. The pressure contributes 2%. R is 0.01 millimeters divided by 0.75 millimeters times 100. And so there's 1.3%. We're gonna multiply that by 4. Okay, so here's where we say, okay, because R has this percent uncertainty, R to the 4th has 4 times that, right? So if we want to take care of that now, there's really 5.3% uncertainty, from R to the 4th. And then L is 0.001 over 0.25 times 100, and so that's just a 0.4% from L. So we add all that up, we got 0.4 plus 5.3 plus 2 plus 0.83. So you should get around 8.5% uncertainty. And if we take 8.5%, so when we divide that by 100 to turn it back into a decimal, multiplied by my calculated value, 1.035 by 10 to the negative 3, then I get an absolute uncertainty. So I have 0.001305 plus or minus 0.1234 zeros, and then 88285, whatever. So 1, 2, 3, there's where my uncertainty is in the 4th decimal place. Oh no, the 5th one. 1, 2, 3, 4. There's my uncertainty there, right? 1, 2, 3, 4. In my 5th decimal point, I should round it there to a 9, right? Round it up. And so that should be it. I guess we could write the answer like, we know it, we know it, we know it, we know it. We could write the answer like that. Have a good weekend, everybody. I'll finish this up. Check YouTube. It'll be up there later. Or Monday, have a good weekend. We'll save it for Monday if you like. 1, 2, 3, 4. And then the 5th one, I think it'd be 0.00131 plus or minus point. That. For a final answer.
Yep. Why would I take AICE now?
Wow. Here we'll go.
Mr. Larson pressure me for that one. I said, no, I'm good, actually. I'm just gonna get it out now.
S. Yeah, 1.04 by 10 to the negative 3. There you go. 8.5, 8.6%. They report the percentage uncertainty, but then they actually converted it into a absolute uncertainty. 1.04 by plus or minus 0.09 by 10 to the negative 3. So that does agree with what we got there. All right, well done, everybody. We'll see you next time.